And now for number 9. Number 9 is super hard, okay? We have that the graph below shows the average savings, S, in thousands of dollars, of a group university graduates as a function of T, number of years, after graduating from university. Okay, cool. So, for part A, we need to write down one feature of this graph which suggests a cubic function might be inappropriate to model this scenario. So let's first talk about what is going on with cubic. See, cubic is to the power of 3, okay? Squared, all right, is to the power of 2. Now, which function have you seen that has a squared on it? The classic, my guy, the parabola, see? So this here usually is like x squared plus 3x plus I don't know what the hell, see? Yeah, this is squared, all right? For a cubic, it would look something like, actually like this one, see? This one right here would be cubic. Now, why is that one cubic? It's cubic because it has this 3, okay? And so depending on whether it has a 3 or a 2, all right, it shows whether it's squared or cubic, all right? You always have to look at the biggest exponent to see if it's cubed or squared or whatever, see? So if the biggest one is 3, that means it's cubed. If the bigger one is 2, that means it's squared. And so one feature of the graph which suggests a cubic function might be appropriate to model this scenario, well, you have to ask yourself, um, what is a characteristic of cubic functions, see? And so, and here's like, I'm first going to give you like a super mega math nerdy reason, and then I'm going to give you more intuitive ones, okay? But a super math nerdy reason is that when you look at any polynomial or any like sort of equation with exponents on it, whichever is the biggest exponent, in this case 3, tells you how many, usually, it tells you how many x-intercepts you have. And so how many x-intercepts do I have here? I have 1, 2, and 3. And so because I have 3, that means I have to have an x cubed somewhere, see? So that is a good reason to have a cubic function, see, because I have 3 x-intercepts. If I have only 2, like in this example here, if you have x squared, how many zeros do I have? I've got this one there and this one there. Ah, interesting. And this even makes sense when you're talking about your classic f of x equals mx plus b. See, your line whatever formula thing. See? Even in your line formula thing, here we have an x to the power of 1. How many x-intercepts do I have? I have only 1, and it's right there. All right? So that is a very good math nerdy reason to say that this should be a cubic function because I have 3 x-intercepts, so then I have to have an x cubed, which makes it a cubic function. Okay, that is probably the best reason I can give you, and also the most math nerdy one I can share. Another sort of intuitive thing, which is probably where most people would go to, is that they know that the cubic function, okay, is basically like an s. Okay, that is intuitive that they have. This is basically like an s that it's on the side. See, now saying that it's an s is not gonna give you a point in the IB. Okay, it's not professional enough. In fact, even in the answer key says, do not accept S shape as a justification. All right. So how can this intuitive S shape be put into fancy math language? Well, looking at the S shape even now, ¿cierto? You notice that you have one maximum here and one minimum there. You have one maximum here and one minimum there. And so you can say that having one max and one minimum suggests that we have a cubic function, which is just another way to say that it looks like an S. I mean, let's be honest. Pero, well, the IB wants us to get fancy, so that's another option. See? I think there was one more, one point of inflection. See, I'm going to go ahead and explain that because, why not? Whatever. But a point of inflection is basically, let's say you have a graph that goes like this. See? So right here, it is growing. See? And then it goes down, and maybe it changes again. See? The moment it changes again, where it goes from growing to decay to grow, if you have grow, decay, grow, that means you have at least one point of inflection. Okay? Because technically this graph also goes like that. See? And so your point of inflection is basically like this part here. That is the intuitive way I can explain it. You have one grow, one decay, one grow. You have 1 point of inflection. See? You have one period of time where it's in decay instead of grow, and then it goes back to being grow. See? All right, whatever. You find the reason that helps you best. For me, it's the S-shaped thing, and you have to just put the fancy math language that you have one max and one min. Those three reasons work. You find which one works for you. That is per day. Then they tell us that the equation of the model can be expressed in the form S equals all of this stuff, where A, B, C, and D are real constants. The graph of the model must pass through the following 4 points. And so these 4 points are real points. Okay, they are parts of my model. For example, 0 and -5 is right here. This point here is 0, -5. 1 and 3, I mean, I'm eyeballing it, but it's probably this. I wouldn't be surprised if it's this. It's 1, 3. See? 2, -1, it's going to be probably here. And 3, -5. Actually, no, I messed it up. Over here, it's probably 2, -1. And over there, it's probably 3, -5. See? Again, I'm just eyeballing it. I'm just trying to explain that these points are part of my graph. See? So you have to work thinking about it that way. All right? So the graph of the model must pass through those 4 points. All right, cool. And we need to immediately write down the value of D. Now, some of you are probably already thinking, how the hell can I immediately write down the value of D? Well, let's look at D in this equation here. X equals AT cubed plus BT squared plus CT plus D. What is special about D that A, B, and C don't share? So D, some of you probably noticed, is alone, okay? D doesn't have a T next to it. Ah, interesting. And so if you go ahead and plug in 0 for T, this point here, if I go ahead and plug in this point there, so we have S is going to be -5 and T is going to be 0. So we have A times 0 cubed plus B times 0 squared plus C times 0 plus D. Now all of these times 0, even 0 times 0, it's just going to end up being 0. So we have 0 plus 0 plus 0 plus D. So -5 equals D. That is the value of D. The more intuitive way I can explain it is that D, because it doesn't have a variable next to it, is going to be your y-intercept. See? It's going to be this guy here. This is no different than when you have, I don't know, 5x squared plus 7x plus 2. And I ask, what is the y-intercept? A lot of you know this by heart, by memory. See? Oh, you say, oh, it's 2. But maybe you don't really get why. Okay? That's because in the y-intercept, all y-intercepts have the point 0, y. So if you plug in 0, y, you're going to end up with y equals -5 times 0 squared plus 7 times 0 plus 2. You end up with only 2. You end up with the one that's alone. You end up with the one that doesn't have a variable next to it. So the y-intercept here would be 2 because y equals 2 when x is 0. Okay? This is no different than what we did just now with point D. All right? I just want to share the intuition that because it's the only one without a variable next to it, it's the y-intercept. All right? Whatever. Fuck it. That is part B, part I. Part B, part double I is write down 3 simultaneous equations for A, B, and C. So, I just used the first point here that I have in red to find the y-intercept, to find D. For the other 3, I can go ahead and use this one, and this one. See? Now, I will tell you right away, this exercise gets messy, and it's an exercise that is supposed to get a little messy. Okay? Point is, I have 3 points. See? I have 1, 3, which is this one here. Then I have 2, -1, which is this one here. And then I have 3, -5, which is this one here. 3, -5. They also tell us that S equals AT cubed plus BT squared plus CT plus D. Now we know that D is how much? We know that D is -5. See, from just now. So we're gonna have plus CT minus 5D. Sorry, minus 5. And so part B, part double I asks us to write down 3 simultaneous equations for A, B, and C. Okay, cool. So I have 3 points, therefore I can make 3 equations. Right, interesting. So this one right here is the same as your x, okay? And in this context, my x is going to be my t. So actually, this 1 right there is going to be t1, and this 3 is going to be s1. All right, this is no different than when I say x1, y1. Okay, it's just a set of points. All right, so t1 is going to be 1, 3 is going to be s1, t2, s2, t3, s3. If you're confused, just follow the process. It's going to make sense in a second. See? So I'm going to go ahead and plug in these points into this equation here. So for the first one, okay, for t1, s1, I'm going to have 3 for s. A is not going to change. And t is going to be 1. So I'm going to have 1 cubed plus b times 1 squared plus c times 1 minus 5. So that means my first equation is 3 equals a plus b plus c minus 5. That is my first equation, and all the equations we're going to put in this purple. Okay, so that is my first equation. For the second one, okay, then I'm going to start over here. My t is going to be 2, and my s is going to be -1. I'm looking at this guy here, all right? So -1 equals a times t, which is 2 cubed, plus b times 2 squared, plus c times 2 minus 5. Notice that I plugged all of these in parentheses, okay? And as a rule of thumb, when you plug in a number, plug it in parentheses. That way you can make sure you're doing it well in terms of exponents, in terms of double negatives, on all of that stuff, see? All right, so -1 equals a times 2 cubed. So 2 cubed is going to be 2 times 2 times 2. If you don't believe me, check your calculator. That is going to be 8. So 8a plus 4b plus 2c minus 5. All right, I'm actually going to leave it like that for now. This is my second equation, see? And now for my third one, we've got that my t3 is 3. So we have, oh, and that my s is -5. So -5 equals a times 3 cubed plus b times 3 squared plus c times 3, -5. I keep going a little bit. I end up with -5 equals 3 times 3 times 3 is going to give me 27. So 27a plus 9b, 3 squared, plus 3c minus 5. All right, and this is going to be my third one. All right, and so that right now, what I just did, is probably enough for part B, part double I. So you write down the 3 simultaneous equations for A, B, and C. And now, hence otherwise, we need to find the values of A, B, and C. All right. And so here, what some of you might have heard of is this thing called elimination and substitution. Okay. When you do elimination or substitution, all you're really doing, and the secret to what is about to happen, is that you decrease the number of variables in your equation. All right, I know what's going to happen now is super messy. It might not make a lot of sense. But at the end of the day, all you're trying to do is decrease the number of variables in your equations. Okay? So I suggest that you're very organized in your approach. Okay? So first of all, let me make a little bit of space and really, really be organized on what you're going to deal with first, second, third, etc. See? So you want these equations to interact with each other in a way that you end up with the least amount of variables possible. See? Right now I have 3 variables and 3 equations. That means I can solve it. Cool. So this first one here, let's leave it a little more beautiful. See? So let's go ahead and do plus 5 over here, plus 5 over here. I end up with 8 equals a plus b plus c. All right, cool. So this is going to be what I'm going to call my first equation. The second equation, let's also leave it a little more nice. So this -5, we're going to do plus 5. Plus 5, we end up with 6. Sorry, hold up. My bad. We end up with 4. Positive 4 equals 8a. plus 4b plus 2c. So this right here is going to be my second equation. And now for my third equation, just to leave it nice, I do plus 5 to both sides. And as you can see, I simply end up with 0 equals this whole thing. All right. So this would be my third equation. Again, I'm just playing around with it so that it looks a little more nice. See? All right, and now that I have it all nice and organized, so you can see that my first equation, I literally called it number 1. Then my second one, number 2. My third one, number 3. Okay, now that I have it all nice and organized, you can really approach this problem in a methodological way and solve it easily. Okay? And so how can we do that? What are my tools? My tools, okay, are elimination and substitution. If you don't know substitution, if you don't know what those are, you're about to discover, don't worry. And your compass, okay, or your intuition, if you want to call it, is that you will do stuff, okay? I'm actually going to put it that way. You will do stuff in order to decrease the number of variables within your equations. So for example, right now, see? Right now, you can see that I've got over here, say, all of these three have A, B, C. A, B, C, A, B, C. I'm going to notice in a second that that is going to change, all right? And the more you decrease the number of variables, the more you will get there, see? And because it's easy to get lost, all right, a way that I'm going to suggest for solving this is that you want to target the second equation, all right? It's going to make more sense what I mean by targeting the second equation. Again, this is just my way of approaching these problems. You've probably got your own. Do what works best for you, see? So I'm going to go ahead and take this first one. I'm going to write it down again. I have 8 equals A plus B plus C. And I'm going to do substitution, see? So that means I'm going to have one of these equations and substitute it into the other one in order to solve it more easily. So let's say I want to get A alone. See, so for getting A alone, I do minus B minus C, minus B minus C. I end up with A equals 8 minus B minus C. So right now I have A alone, and I'm going to call this 1 prime. So 1 prime is going to be this here. It is A equals blah, blah, blah. I call it prime just to be organized and know like, yo, this is an equation that I edited. Okay, it's modified. Again, it's just a way to keep things clean. It's just how I do it. You find your own way. So I'm going to go ahead and plug in 1 prime, okay, into the second one. So you plug in 1 prime into the second one, you're going to have 4 equals 8a. Now we know that a from substitution, ¿cierto? From 1 prime is this. So 8a is going to be 8 minus b minus c plus 4b plus 2c. And I know this looks kind of nasty, but trust the process. It's going to work out. 8 times 8, 64. 8 times b minus 8b. 8 times c minus 8c. Plus 4b plus 2c. So let's combine like terms, leave everything kind of nice. I'm going to do minus 64 to both sides. I end up with minus 60 equals b with b is going to be negative 4b. C with c is going to be negative 6c. And so this right now is sort of like an equation I have. See? Now what is special about this equation? See? Notice, up here I had 3 variables, 3 variables, 3 variables. How many do I have in this green one? Ah, you have just 2. You have B and C. So what used to be A, B, and C is now just B and C. Hence the compass or the intuition I was talking about. You want to decrease the number of variables, and that way you end up with just A equals something, or just B equals something, or just C equals something, and it'll work from there. See? And so right now I sort of, and again, this is just how I like to solve it. You targeted the second equation. See? You took the first one, you edited it, and you plugged it into the second. So now we're going to take the third one, we're going to edit it, and plug it into the second one. That way we keep targeting the second equation. This is just a very intuitive way for me to explain it. You do your own, okay? So I'm going to take the third one, which is 0 equals 27a plus 9b plus 3c, okay? And so 1 prime got A alone. We're going to do that again. Okay, 3 prime will get A alone. So for getting A alone, I have 27A equals negative 9B minus 3C. So A equals negative 9 divided by 27B minus 3 divided by 27 times C. Those fractions look kind of weird, so I'm going to go ahead and simplify a little bit. This first term is going to turn to negative 1/3 B, and this second one is going to turn into, I'm pretty sure it's 1 over 9C. Yes, it is 1 over 9C. And so this here is going to be what we're going to call 3 prime. Okay? So this is 3 prime. I'm going to box it in red. And again, notice how both of my primes have an A equals something. Okay? So I'm going to go ahead and take 3 prime and plug it into 2. Thus, the target, the second equation thing I was talking about. See? Right now we're doing the thing on the bottom. We already did the thing on the top. Yep. So we keep targeting the second equation. We plug in 3 prime into the second one. See? The second one up here. So we end up with 4 equals 8 times A. Now because of substitution, A is going to be whatever that is. See? It's going to be negative 1/3 B, negative 1 over 9C, close parentheses, plus 4B plus 2C. Cool. So 4 equals negative 8 divided by 3B minus 8 divided by 9C plus 4B plus 2C. All right. So I don't like these fractions. See, so in order to get rid of the fractions, for example, I can multiply everything by 3. See, so I go ahead and multiply everything by 3. I am basically targeting this 3 here, all right? So I target this 3 here by multiplying everything by 3. I end up with 4 times 3 is 12. Actually, I'll keep going with the dark color. 4 times 3 is 12 equals negative 8b, so that fraction disappeared. Minus 8 times 3 is going to give me 24 divided by 9c plus 4 times 3 is 12b plus 2 times 3 is 6c. Now I still have a fraction going on which I don't like, so I'm going to multiply everything by 9 now. Okay, this is just a trick to make my numbers a little more pretty, although bigger. 12 times 9 is going to be 108 equals 8 times 9, which is 72 minus 24c plus 12 times 9, I think I just did that now, 108, 108b plus 6 times 9, I think it's 54, yes it is, 54c. So now I can combine like terms, so 108 stays alone over here. B with B is going to give me, so it's 108 minus 72, it's going to give me 36b. And combining the c's, I end up with, I think it's half of it, 54. It's just going to be 30. Okay, cool. So I end up with plus 30c. All right, and now, ¿cierto? I have these two sort of equations. Both of them have just b and c. And so now I can make these two green guys interact, ¿cierto? Which is what was cool about targeting, quote unquote, the second equation. Always making sure that your primes, the 1 prime and 3 prime, have the same variable being equal. So a equals something, a equals something. You plug both of those into the second one by targeting the second equation, you're going to get somewhere. See? So now I'm going to write down these two equations over here. All right? We have negative 60 equals negative 4b minus 6c. Right below, we have 108 equals 36b plus 30c. And I want to combine both of them. See? So what I can do here, just thinking out loud, I can do elimination now. See? This whole time I've been showing substitution, now I can do elimination. When you do elimination, basically, you want to add both of your equations and have one of the variables eliminate. If I do that right now, none of my variables get eliminated. But if I change the one up top by multiplying by 5, okay, so I multiply everything by 5, you're going to see that I end up with, well, negative 60 times 5 gives you, I'm pretty sure it's 300, but I just really don't want to be wrong. Okay. It's negative 300 equals negative 20b minus 30c. 6 times 5, yes, negative 30. And down below I have 108, the one that didn't change, ¿cierto? 36b plus 30c. And so now if I go ahead and add both, you're going to see that one of these guys gets eliminated. Negative 30c plus 30c, it's going to be 0. See? So what do I end up with? I end up with negative 300. Oops, negative 300 plus 108. Da, 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 negative 192 equals 16b. Ooh, now we're getting somewhere. So 192 divided by 16b is going to give me negative 12. So b equals negative 12. So finally, damn, after all of that, we got somewhere. See? I know it took a long time, but if you follow the process really well, which is this whole targeting thing, okay, and keeping in mind that you want to decrease the number of variables, okay, from A, B, C to just B, C to, in this case, just B, you're going to get somewhere. See, so now I just got B equals negative 12. So here, once you get B equals negative 12, or likewise, okay, you just plug that shit in flipping everywhere, okay? So I'm going to take this negative 12, I'm going to plug it into this one, see? So 108 equals 36 times negative 12 plus 30c. Boom. How many variables do I have here? How many? How many? How many? Just one. I've only got c. Beautiful. So I just work around until I reach c equals something. So 108, that is supposed to be a 0. 108 equals 36 times 12. That's a fat number. Negative 432 plus 30c. So I'm going to do plus 432 to both sides, plus 42 to both sides. C is going to be equal to 432 plus 108 gives me 540. C is going to be equal, 30C. Divide by 30 to both sides, divide by 30 to both sides. C equals 14, 18. C equals 18. Boom. So B is 12, C is 18. Now I can plug it into the first one even. So I'm going to go into the first one with all the stuff I know now. So A is A, B we said was negative 12, C we said was 18. So negative 12 plus 18, 8 equals A plus 6, means that A equals 2. Bada bim, bada boom. We check the answer key just to double check. A is 2, B is negative 12, C is 18, ladies and gentlemen. See? So I know that was a long process and etc., but you can always solve it the same way. See? Consider the prime thing, all right? Consider attacking the second equation. In my experience, it's the best way to do it. And more importantly, the math lesson behind all of this is that elimination substitution, what's cool about it is that you decrease the number of variables, and that's what truly helps you solve this, okay? So yeah, that is for part B, part 3, finding the values of A, B, and C. And now it gets super weird. See, they tell us that a negative value of S indicates that a graduate is expected to be in debt. Okay? And we need to use the model to determine the total length of time in years for which a graduate is expected to be in debt after graduating from university. So, S is average savings. See? So if S is negative, okay, that means that you will have negative savings, and negative savings means debt. So consider in this graph, where in this graph do I have an S that is negative? Because S is my Y value, ¿cierto? If I have anything above S, I mean above the 0 is going to be positive, and anything below over here it's going to be negative, all right? So depending on whether I'm on top or below the x-axis is whether it's positive or negative. So this guy right now is in debt here. Here they're in debt. From here until here, they're in debt. Later on, they're in debt from here until here, they're in debt. See? And so what part C, it was part C, right? What part C is asking for is the total length of time for which a gradient is expected to be in depth. So basically, I need to find the time from here to here and add it up, and then the time from here to here and add it up. And then they're not in depth anymore and they can live a happy life. Not very realistic in terms of depth, but whatever, it's fine. Okay? So we want to find these two values for t and these two values for t, and we can go ahead and just add everything. See? Now, there's a couple ways to solve this, and what I think is the most intuitive is using the graphing calculator. And so because I found that a is 2, that b is negative 12, give me a second, sorry. Yes, b is negative 12, that c is 18, and that d is negative 5, I can plug it in here. See? So that means that my savings function is 2t cubed plus, or sorry, minus 12t squared, I forgot the cubed, plus 18t minus 5. This is an s, by the way, okay? So this is my function, all right? And because I need to find all those points here, I need to plug in 0 for s, see? Because what all these points have in common is some t value and a 0 for s, okay? So what I can do, interesting, is go ahead and graph it, see? So I can go to y equals and graph this whole thing. So I'm going to take 2x cubed minus 12x squared plus 18x minus 5. So I go ahead and graph. My graph is probably not going to look that nice. Okay, that is all right. No worries. Go ahead, I'm going to change my window a little bit, change the zoom in particular, zoom fit, see what happens. All right, so this window is a little messed up, but that is fine. So my y minimum, we're going to go ahead and change it to, yeah, we're going to change it to 8. Maximum, we're going to leave it at, I don't know, 3. And then these two values, let's see how it ends up. All right, so I can almost see the points I need. See, I have the first 3. I need the last one. So I'm going to change my x value, x max, to, I don't know, 6. Maybe now it works better. All right, beautiful. And so now I can use a whole bunch of calculator functions and stuff and etc. to find the zeros. See, to find these 4 points. All right. Well, I really only need to find 3 points, but to make the window even nicer, see, I can get rid of my negative x values and maybe change my y min to, I don't know, 6. All right, that makes it a whole lot nicer to work with, see? And so now, in order to calculate the time, I know that this point here is the origin, see? So this point is 0, 0. Let's find the other 3 points, see? For this first point, what I can do is use the zeros function, see? So I'm going to go second and trace and hit that calc and press 0 because I'm trying to find the 0, see? Zeros in your calculator is the same as, quite simply, an x-intercept, see? So right now it's asking for left bound and right bound. What left bound and right bound does is that you're telling your calculator from where to like scan. See, so I want this calculator to scan from over here, right bound over here. See, then it asks for you to guess. All that guess really does is specify your calculator which 0 you want. Okay, so as long as you put your bounds well, you're gonna get it correct. The 0 over here is, give me a second. The 0 over here is 0.358, comma 0. So that is this point here. What about the next point? Well, let's do the same process. So left bound, we're going to get it a little closer over there. Right bound over here. And guess right there. All right, so this over here is 1.83, comma 0. And this last one, okay, is going to be finding the zeros, left bound, all the way there, right bound. We do the guess where we want it. It's around here. Boom. This right here is going to be 3.811, comma 0. All right, so basically from here to here, he was in debt. And from here to here, he was also in debt. Okay? That means that he was in debt for initially, ¿cierto? For this first part, he was in debt initially for 0.358 years. And then he was in debt for this distance here, ¿cierto? I'm going to go ahead and do 3.81 minus 1.83. All right, for finding that distance there, it's going to give me, let's find out. So we end up with 0.358 plus 3.81. That's fine. Minus 1.83. 2.338. 2.338. So basically, for this last part, using the model to determine the total length of time in years for which credit is expected to be in debt, it is just around 2.338 years. All right. So that is for number 9.